really good.
Ah,
Okay.
the
Saw the
meeting is
announcement.
being live streamed.
Okay, we are being live streamed, so let's stay lively.
And watch your language. Or not, depending on, you know.
So we got an April 17th, Los Angeles Astronomical Society General Meeting, starting at 8:02. Welcome, everybody. How's everybody doing? Looks like we got a good crowd tonight. Yeah,
Doing
everybody
good,
thumbs
Daryl.
up.
Yep, doing good.
We had a really nice star party up at Lockwood on Saturday, which I went to, which was rare for me because I'm usually at Mount Wilson. But the 100-inch night was canceled, so I went to Lockwood. So it was really good. Hadn't been there for a while. So I had a great time there. Let's see. I don't have any great big announcements. Oh, we have one thing that we have to do for
New
an
members?
honorary lifetime membership for Shirley. Is that correct?
Right.
Yeah,
Okay.
Shirley
We'll do
Sonata.
that during the secretary's report.
We can do it whenever you're in the mood.
Okay.
You didn't talk about the public star party coming up.
That's the second, not this coming Saturday, but the following Saturday
29th.
at Griffith. Will be star party. We'll be there in our glory. If the weather's good, we'll bring out the pop-up tent that we have. Also being some filming done there that day. So maybe we'll get on camera yet again this month. That would be great.
Joe, I'll
Let
be
them
ready
know
with
about the
26 again.
I'm sorry, say again?
I'll be ready to operate the 26 with Joe if he wants to do it.
Okay.
Yeah.
Let them know
Great.
about signing the agreement, signing the film agreement too, if they want to be filmed.
Right. All of the volunteers that are there, if they come up to you and want to film you, you need to sign a release. And if you don't want to sign the release, that's fine. They just won't film you. It's not a big deal, but just know that they'll ask you for a release if you're going to be on camera. Pretty standard
Who's
stuff.
filming?
Pretty standard stuff.
It's Griffith is doing a small video piece on just to publicize the observatory.
Cool.
Just promotion, yeah?
Yeah.
Yeah.
Okay. Anything else? Any new members here that I haven't seen before? We have a new member tonight. Anybody new? No.
Andrew's raising his hand.
Andrew?
Andrew Jones.
How you doing, Andrew?
Good,
tell us
good.
just
Can you hear me?
Yeah, sure. Tell us just a little bit about yourself. What's up?
Well, my wife, Veronica, she's teaching a class right now, but she'll be in around 9 o'clock, so you may get to say hi to her as well at the end of the night. But we're having a good time. We're both in television for our careers, but now we're doing real estate, so don't talk to us. But we decided we were getting boring and all we were talking to was real estate people. And I think we were both always interested in astronomy. So here we are, and everybody's been very nice. You can see the 6-inch Dobsonian back there that we just got on your loaner program. Thank you, Keith. I saw you somewhere. I did get the scope collimated. I actually did it myself, and I think I got it pretty good. But when I got out to Lockwood, Andy jumped right in and whipped out his laser and fine-tuned it for me.
Awesome.
It wasn't that scary at all.
Right.
And we're here to play. It's we'll be around.
Good.
Welcome aboard.
Yeah.
Glad to have you here. Glad you're already using the loaner program. Saw you at Lockwood. That was great. Everyone's having a good time up there too. Good.
Yeah, it's a nice place. We actually went out there the week before and hung on the fence, and definitely we're ready to go by the time the gate opened. Here you go. There's our
Hey, got your pins.
There's our brand new membership pin.
Yay.
All right.
Yeah.
Very
All
good.
right, Spencer, doing your job.
Yeah, that's right. Good job, Spencer. You got them off the kitchen table there.
It takes a while to chisel those out.
Yeah.
Laser out.
I got a piece of information about Lockwood. Alicia emailed me today and said that they did come out and pumped the holding tank yesterday
nice.
or today, maybe today. The guy called me up. He's back. He was back from his couple of days off in Laughlin, and so they came out and did that today. So we're ready to go for a long time.
Good.
Any word on the water facility there? The guy with the water?
I haven't heard from him, but I took a walk and realized that the well that's on the other property is it's probably less than 100 yards from the caddy corner from the corner of our property. So it's really close. I don't know what good that is,
Yeah.
but it looks intact and it looks like it just needs to be plugged in and see if it runs. And
Can we drill a hole into it with a hose?
I'm sorry.
We can drill a hole into it with a hose. I'm just joking.
No,
Sorry.
I mean the water pipe comes out. I mean if the pump works and it's still in the water table, I mean there's a big PVC, piece coming out of that that's broken, but water comes out, water comes out. But if I can't ever get a hold of the guy that owns the property, I might happen to go over there with a generator and turn it on once in a while and fill up our tank. It's not that far away. And generator for the power and a good size hose, 100 yards or so. Anyway, in the back of my mind, if we get low on water and we can't use our, for whatever reason, we can't use our other resource that will deliver.
Was that,
Any other new members?
yeah, was there
Any other new
another
members tonight?
Probnor?
Yeah, hello everybody, my name is Probnor. I'm currently a 10th grader, 15 years old. I recently got interested in astronomy around 2 months ago when I got my first telescope, and I was just amazed of what I could see through it. So I wanted to expand my astronomy journey and looked into joining local clubs, but there wasn't around any in my area. So I looked into through my teacher. So he made me found the Los Angeles Astronomical Society, and it's an honor to be here, and I'm great that I joined.
So where do you live that you couldn't get to another club?
I live in Sun Valley.
Oh, I guess there's
Not too far from me.
nothing particularly out that direction, is there?
Yeah.
Well, welcome to this club. We'll welcome you in. That's fantastic. Glad to have you here.
Thank you.
Is that up near like the Santa Clarita area?
Don't
It's-
help them out,
it's
Tim. We want
near
them in our
Burbank.
club.
Well, you can join 2 or 3 clubs. Nothing wrong with that. I think
Right.
that's where the local group hangs out in the Santa Clarita area.
Okay, I think that's all I can think of for big announcements for me.
I think we still have some more new members.
I'm sorry?
I think we still have some new members who haven't chimed in.
Oh, I'm sorry. I didn't see hands go up. Is there another new member? I don't recognize. Kathy, are you a new member?
Sort of new, but
Sorta?
but I've been to a couple meetings before.
Okay.
But yeah, I'm just super interested in astronomy, and I was given a 4-inch beautiful telescope that I am trying to learn how to use, and I found your group and learned that there was maybe some help if I take it with me up the mountain, and so I'm looking forward to doing that.
Well, the help would be at Garvey Ranch, not up the mountain in Monterey Park.
Yeah.
Oh,
We like
where's
new
the help?
members that we can indoctrinate into the skill.
Oh,
There's almost
welcome.
always somebody at Garvey that knows about telescopes. So
Any Wednesday night, Kathy, we'll be happy to get you going.
okay, I'll look on the site and get the info for that.
Yep, absolutely.
And usually
Monterey.
at Lockwood, people are involved in their own programs and equipment. So, but at Garvey Ranch, that's not the case.
Perfect for there.
Yeah.
You can come- you can
Any other members that I missed that were just newcomers?
So I got a hand
We've
up
got
for
3
Greg.
pages.
I'm not necessarily a new member. I've been a member for almost 2 years now, but this is the first meeting I've finally been able to attend. I've been to a few dark sky nights and a few outreach events and really enjoyed those. But
Nice.
so I have to finally attend a meeting, and I haven't been out to Garvey yet, too. That's next on my to-do list, and then I'll
Great.
have come full circle. So
Good. Come hang at Garvey. There's a lot of good people there. Never a dull Wednesday night, that's for sure. Okay, anybody else?
Thank you.
How about the oldest member? No, no, no. Let's not go there.
Don't we have several candidates for that? I'm seeing
No,
some
no,
right
no, no.
now.
I just said let's not go there.
That's furry face.
We won't have any kind of a treasury report. I think John was going to prepare a kind of a abbreviated report for the general meeting because you don't need to know all the details. But he is out of town on a medical emergency. Spencer, is there anything you want to say for the secretary's report? And maybe we could bring up Shirley.
Yeah, sure. So we, as of tonight, we have 1,023 members.
What?
And since I closed out the new member list at the let's see, on April 5th, we've had 7 or 8 more applicants that are in the queue right now.
Wow.
Nice.
So it just keeps coming in. So it's great. And I think so. I guess the next thing is we want to talk about a life membership for Shirley Sonata. Tim, you want to give the introduction about Shirley?
Oh, well,
Actually, let me start. Let me preface this. So according to our bylaws, the board can nominate somebody for life membership, but then it has to be approved by the general membership. So that's why we're bringing it up here. So go ahead, Tim.
yeah, well, I came into the LAAS in 1987 because I was the last president of the Monterey Park Astronomical Society. And when we were assimilated into the LAAS, the denouement of that society, I started. And Shirley was already a member of the LAAS. I think she joined a few months before I did. She lives very near Garvey and has been our welcoming person and was opening the observatory for years. But she's in her 80s now and she doesn't get around quite as well as she used to, and we don't see her as often as we did. She does still show up, but she's been around for a long, long time and has really been a big help to the society. And I actually nominated her for a life membership so she wouldn't have to pay dues anymore. And I think she deserves it personally.
It's a great gesture from the club. She's been solid as a rock at Garvey for as long as I can remember.
Decades.
Yeah. She was opening every Wednesday when I started coming there. Anyway.
Then she brings Seas Candy.
So we're going to put it up to a vote that we extend a lifetime membership to Shirley Sonata. Everyone in favor? Clap, say aye.
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 Hey,
Aye.
cacophony of ayes. Fantastic. Any nays? You better not. Okay, good.
That's the way to have an election. You better not.
Okay. So how do we spring this on her the next time she shows up, or do you want to contact her?
You probably have to send her a letter because she doesn't read her email anymore. And I'm sure she has 15,000 messages in her queue. She hasn't even opened it in like 3 years or something.
Okay.
Best thing would be to contact her.
Okay. Well, if she's at the address that she's in the roster, I can send her an actual mail.
That's probably a good thing to do. Her telephone number is actually the same, believe it or not, as a travel agency. And it's 50-50. When you call her phone, you'll either get her or you'll get the travel agency. If you hang up and dial again, then you'll get her. I've done it, it's crazy.
I love it. Okay, that's great. Anything else, Spencer? You got an update on the dark sky stuff? You made some. We made some progress there, yes?
Oh, on the for the Lockwood Committee?
The dark sky.
No, for the dark sky.
I'm
Light
sorry. The light pollution. Yeah.
The light pollution.
Oh,
Sorry.
the light pollution. Okay. Right. Yeah, it's a really a lot of really good progress. So we've been meeting with Rod Kaufman. I've been meeting with the LA County Regional Planning Departments. And so their director is really on board. I mean, I think it was just such a stroke of good fortune that she accepted our invitation to visit visit Lockwood and was able to see firsthand the effect of light pollution on the Milky Way. And then the fact that the rod had his, I think it's 16-inch or 16 or 17-inch Dob, and was showing them Jupiter, and it was so bright that you could actually see Jupiter projected onto people's faces. So, and the woman's daughter is also interested in astrophysics and astronomy, so that helped a lot. But anyways, so they have basically, she's directed that all new permits for unincorporated areas that have to go through them for review adhere to dark sky standards, and so they've asked us for input on what the language should be in terms of types of lighting that's permissible, color temperature, things like that. So that was effective immediately. And so then the other thing that they're doing is they said that since the ordinance was passed in 2011, there have only been 4 complaints about dark sky, about violations of the dark sky ordinance in the unincorporated areas. And so that obviously points to an educational problem. So there are 2 efforts going on along that line. The person who develops videos for the county is interested in promoting information about the dark sky ordinance. So he's done his own series. He's working on his own videos. And at the same time, they've asked us to help them prepare, the county regional planning folks have asked us to help them prepare a brochure that they'll mail at their expense to all the residents in the unincorporated areas of LA County, explaining what the
Hold on a
ordinance.
second.
Yeah.
Andrew, do you know that you're sharing your screen?
Yeah, that's a picture of the sky glow from Los Angeles that I took the week before the dark sky night up at Lockwood.
This is from Lockwood. Okay. All right. I just didn't understand what was going on. I'm sorry, Spencer. Go ahead.
All right. So anyways, we're getting materials ready to help them craft a brochure that they'll send out to residents in unincorporated LA County. And there's some other things that they can do in terms of just administratively to further the dark sky ordinances. So that's very good news. And then they have long-term plans about perhaps changing and expanding the ordinance, but that's, we're talking a really long-term horizon on for that effort, because it's going to have to go through a lot of bureaucracy and several levels of administrative review, things like that. But I think, we're off to a good start.
And do we not have them invited up to the 60-inch to see how bad Los Angeles has gotten?
Yeah, so I've extended an invitation for the 60-inch. I think they're looking at making the July 60-inch session.
So that would be great. So they've been to Lockwood, and then they can get to, if they see what Los Angeles looks like. Nice contrast there. Great.
The other thing that, we haven't had much luck trying to get anything done at the state level, because we missed the cutoff. Well, the cutoff for introducing new legislation was February, but and I think each state senator can only introduce 10 bills per session. And so this wasn't high enough on their priority list to make it for this session, but we'll try again for next year.
Okay. All right. Good. Do we have any other announcements from Mount Wilson, Tim, other than they're open and sessions are starting again?
Yeah, I mean, Mount Wilson is, I hope next weekend we'll be able to open for regular tours. At least that's the schedule so far.
Including Cosmic Cafe too?
Yeah, that's one of the reasons they were worried about safety on the grounds, but they have to have the Cosmic Cafe to sell tour tickets and for the tour guides to get their keys, et cetera, et cetera. And I should say, and a little bit of, self-aggrandizing, that I will be the first speaker in the Talks and Telescope series on May 27th about the James Webb Space Telescope. So go to the Mount Wilson Observatory webpage and look for events and look for the Talks and Telescopes. And the first one in May will be the James Webb Space Telescope, and I will look just as brilliant as I always do. But anyway, there you are.
Isn't there a few spots left open for the 60-inch?
Actually, at this point, I don't think so. I just got a slew of emails and took care of that before I came on here, and I think I'm up to 22 or 23, so 25 is max. I mean, I'm expecting by the end of the meeting that I'll have another couple of emails for requests. I asked Andy to send out a blast. There was still some
Yeah.
openings. By the way, all the rest of the 60-inch nights have openings. The second 100-inch night, however, is already full because all of the people that got canceled on the first 100-inch just moved everybody over to that night. So that worked out okay.
Any word, Daryl, question, any word from Mount Wilson about resuming star parties for us?
They are on board. They are on board with resuming star parties, as far as I know, with either concurrent with the 60-inch nights.
That's the way we've done it.
It worked out okay last year, and I think, I mean, we have permission to do it. So if we have the personnel and a couple of people to do the parking lot and take care of ourselves up there, then we have the permission to do it. So any 60. What's that?
That's usually the week. That's usually the week before the Griffith Park observatories, right? Is that correct? The week before.
Yeah.
Dark night. They're concurrent with the LAAS 60-inch nights, and that's usually done by. So it's Lockwood, the public star party, and the 60-inch all at the same time.
Right.
Okay. All right.
We should probably get that on the calendar and talk about publicizing it a bit and get
Which
organized.
is that?
Yeah, the if we're gonna do the public star parties at Griffith. I don't.
Oh, yeah, but almost all of that is Andy giving a blast, and the rest of it's social media. Almost all, last year,
All
we really got great responses from social media. So I'm expecting it to be at least as good or better this year. So I think we need to be ready for a lot of people, because the last time that we had a good night, which was actually both of the nights that we had were very good. I was astonished. I was at the 60-inch, so I wasn't there right at the beginning, and I just took a break and I came out to see what was going on. I could not believe that the entire parking lot was full of cars and people were waiting for someone to leave out of a space to go and park. This is a spectacular response.
It was really cold too. It was cold.
That's right. That's right. We weren't expecting that many people because it was cold. Anyway, and how good of a time did everyone have, Keith? A great time.
Yeah, for that, I had FOMO from being in the in the 60-inch with you. I kind of like the party was outside.
That's right. Well,
Yeah, well, I was with a 100-inch session on one such night, and I remembered seeing that line trying to get into the parking lot. And then when I left shortly after midnight, I glanced over there and I said, the parking lot is totally packed. And then I realized I'm leaving at the right time. Can you imagine all those people leaving at 1 at the same time? I don't even want to think about it.
okay, let's not. Okay, is there anything else?
Okay, Daryl?
Yes, sir.
Yeah, I got a little bit of an update for Ford.
Okay, fantastic. Let's hear it.
Okay, I went on the road this weekend and got about a quarter mile up before I got a blockage on the road. So I had to turn my Hummer around and leave. But Joe Phipps and I are going to attempt to get the observatory open for Memorial Day weekend. And
Well,
also,
you couldn't push it out of the way with you.
Yeah, I'm gonna get a hold of. I'm going to try to get a hold of the forestry and find out if they're planning on doing anything to maintain the road, find out what they are be willing to do, because there is some activity on the road. There's people cutting some branches, doing some cutting and that kind of stuff, but there's a lot of debris on the road right now. But Joe Phipps and I are first chance we get an opportunity to get up there. We're going to try to implement Ford, try to make Ford a little bit more user-friendly for imaging up at Ford. So we're going to see what we can do to make Ford a little bit more accessible for imaging and stuff.
Curtis, if you're going to do that, I still have the 15-foot cable that I paid for, and I'm willing to install up there. Probably for me, the best time might be Friday.
Well, we
in the
could.
daytime.
Well, the thing is we're going to get an ASI Air, so we may not need it.
Okay, but it's there. I still have it.
If you got it, keep it anyway, just in case.
I'd install it just to make sure A, that it's working, and B, it's available for backup.
Yeah, we can do that. That's not a problem. But Friday could be a little bit, you just have to let me know ahead of time so we can go up early. So,
All right, well, let us
But we
know
gotta
when you
get it
have
open.
let us know
We
when
gotta
you know
get it
you have
open
the
first.
event and we'll put it in,
yeah, as soon as we get something, we'll let you know.
very good.
Okay.
Okay. Any other announcements that we need to do? Otherwise, I can hand it over to, Greg, you want to talk about the Boy Scouts?
Yeah, real quick, just to let the club know, our astronomy merit badge classes this summer filled up right away as they have in years past. So we have Wednesday night at Garvey in June, July, and August. I'll send out the flyer and get it in the bulletin. On those nights, it's really great to have support from club members willing to bring their telescope out to Garvey on the lawn, because we have scouts and it's summer, so we're usually a little bit busy at Garvey. Anyway, it's been a really successful program, and it continues this summer starting in June. That's it.
What Wednesdays are those?
It's like the 15th to 17th, and I think the August one is like the second one. It's like the second or third Wednesday in each month. I'll publish out the dates. I don't have them right in front of me. But they went up on the council website and the classes were full in like 24 hours. So people watch that, and word of mouth has gotten around amongst that community. As soon as it goes up, people grab all the slots, which is good. Popular
Good.
program.
No, it's popular. That's good.
Oh,
Yeah.
one quick update on Lockwood Valley. So
Sure, go
okay, so we had the Lockwood committee had a small work party there on Friday on before the star party, and we basically cleared out the area where we're going to put the second roll-off observatory. And so that's all clear. We did have to, we had a problem with water freezing. And so the result, we had a flood in the bathroom, which we cleaned out and got the toilet repaired just in time for the star party to start. So we'll probably schedule another work party sometime later in a month or two to do some weed clearance. So we'll send out an announcement for that. And I know Roman's been working pretty hard on getting the the specs and things like that for the remote operation observatory. So I think Roman, check me, but we're planning on sending out a survey to the membership to get some guidance on the type of equipment we're going to be buying, right?
Yeah, we're in the final throes. We're trying to get the wording out, and hopefully in a couple of weeks we'll get a poll out to kind of get some feedback from membership and move out from there.
Okay. All right. So stay tuned.
Hey, speaking of Lockwood, do you think that's possible that we could open up GMO for the May 13th family night? Are we brazen enough to try it? You got the lid off it.
Yeah, I don't see any problems with it. I would probably go up there the day before just to make sure.
I would be happy to go up there on the 12th to make sure that it's not going to be a disaster. But yeah, I'd like to take a crack at it.
Okay. Yeah. Okay. So I'll probably see you out there since I need to do an overhaul on the Wi-Fi network there. Anyways, I don't want to do that during just the night before a star party.
Yeah, for sure.
Well, good. Thank you, Keith. I'm glad you're interested in keeping that rolling.
Oh no! Once we got the lid off of it, I felt like Indiana Jones, like rolling around in there. Like it was like a tomb, but it was clean. It was a clean tomb. So, yeah.
I saw your write-up about the night. It was really great. Thank you for being as eloquent as you are.
Nice work on that, Keith. Very nicely done.
Yeah. It's real. It's very real. It's not. I don't know how else to describe it. It's very real responses, and I like them. So, don't stop.
Okay, you got it.
All right. Well,
I got three things.
Yes, Nick.
So Luke Chilton, I talked to him on a couple of occasions, and he brought up persistently the notion that, and I'm not taking a side or pushing an agenda or side, but just to put out there to the club that we used to meet at Garvey for our general meetings, and then he's concerned that the longer we stay in Zoom, that the higher the chance that it will be that we'll never be able to go back and have the option to go back to reclaim Griffith for our general meetings. I am sure it's an ambivalent group in here. I think I enjoy definitely being at home, but I definitely wouldn't like to lose Griffith permanently as an option. So I'm bringing that up on behalf of Lou.
Well, let me do a quick poll right now. There's enough people here. We got 52 people here. How many people want to start having our general meetings again, back in person at Griffith? Greg, can you take a look and see how many people this is going to be? 2 hands for Brian. That's 2 votes there. Let's see.
Is this a non-hybrid?
Let's use the reaction tabs on the Zoom there so I can see the yellow hands.
Yeah, okay. Yeah, hands up, hands up, hands up. Do you guys all know how to put your hands up or a thumbs up?
Yeah.
I have a question. Would it still be broadcast?
Yes.
Yeah.
Yes. Look, we've made it clear that we intend to still broadcast and still be able to do Zoom for our members. I mean, for the members and for the guests, if the guests can't be there in person. I talked to Evan on Wednesday night, and he knows how to do that, and he will be there anytime that we are there. So we are good to go on that.
We are okay on our side, but the Griffith people are discussing that. I've been in touch with Mark Pine a few times, and they're talking about it. They're not.
I thought they were only worried about having the personnel. I thought they were only worried about having the personnel for that.
No, when I talked to Mark Pine, he said he had to go back and talk to Krupp and the others again. And they know we have members who can do it, but they're always worried about scheduling and staffing and a whole bunch of other things. It's a city bureaucracy. And so we're not going to lose Griffith. That's not going to happen. It's just that we're dealing with the bureaucracy, and it moves with the speed bureaucracies usually move at, which is,
Okay, so the ball is in their court. We are saying, yes, we want to come back, but we want to confirm that it's going to be still Zoomable in and out, which they can do. We've seen, events from there. We know they can do it. Evan can run it and is volunteering to do it anytime that we have a meeting there. So we have the staff committed, and we have enough people want to do it. I think that we should go ahead and start it again. But we're just waiting for Griffith to say, okay.
And Daryl, some people dropped in and out as Zoom is interactive, but I think the count's right around 25. So it's like almost exactly half the members present voted for it. Yeah.
I think it's a good move. I mean, personally, I can make it. It's close for me, and it's not bad. But I think a lot of the new members would have a good, chance to meet people in a different way if they can't make, a Garvey on Wednesday, and, see what we do there too. So I'm for it. So we're waiting for Griffin.
Yeah.
And of course, because it came from Lou, it came in the context of all this deep history and all the associations, and just, by the time he was done talking about it, I felt like I wanted to carry a torch in there and really just say,
everything is historic for Lou.
This is ours. Yeah.
That's his job.
Yeah.
Well, he's the historian. He can make anything historic.
The other 2 things I want to say is I would like to I think all of us are thinking it. I would like to recognize Keith. He, it's his anniversary. He became a star member. So congratulations. Woo, and I know he's excited. Now he can go up there. I just want to say that you have injected so much enthusiasm. You go to all the outreach events. You've brought in a lot of people. And I think the energy, at least for my part, I'm very much enjoying the fruits of your Brian's labor, because we see all these new people out there and they're just very excited. And I think that takes a lot of energy. So thank you to you on that.
Thanks a lot, Nick. Hey, it's everyone there. It's just basically just stirring up the pot just to make some bubbles happen. That's all. I'm just trying not to stargaze by myself. Is that still wrong?
No, we love it, man.
Congrats.
Okay, I guess there's some real feedback coming in here. Is that Kimberly? Is that you? Maybe. Okay. Spencer, do you want to put up
Sure, yeah,
the slide up for our speaker? And,
yeah, let me share the slide for the speaker.
And Tim, go ahead and do the introduction because I don't think I know this name, so I'll be being introduced as well.
Well, Barujan
Okay.
has talked to us before,
Okay.
usually on black holes, exoplanets, something or the other. He was a colleague of mine back when dinosaurs roamed the earth before I retired and worked at JPL. And he started out infrared astronomy. He's done, I think, cosmic microwave background, but active galactic nuclei has always been a thing that he's been working on for ages and ages. And so it's really like pulling teeth to get him to talk about it. You know, it's I managed to pull it off. And,
yeah, Tim, I want my cat back, when I give this talk.
okay.
All right. So okay, I'm gonna stop sharing. You can share your screen.
Okay.
Good. Let me start. Thank you, Vajan, for doing this. So everyone mute so we can have and put questions in the chat, and we'll try and get those, and we'll leave some time at the end for.
Yeah, I mean, I think over Zoom that works a little bit better to have the questions at the end. But if you don't want to forget your questions, please feel free to put them in the chat. And Tim is, of course, being way too kind to me, but and he was a great colleague at JPL, and it was sad to see him retire. But that also tells me that he did mention that we started in the age of dinosaurs. But yeah, that ages me as well. So let me share my screen. Hopefully everybody can see it.
Yeah, we're good. Full screen.
Okay, so I noticed that there's a fairly wide range of sort of newer members who are just coming into this and members who've been around for a little while. But the main thing I wanted to talk about is how black holes feed, and in particular, how these supermassive black holes at the centers of galaxies, which basically when they feed, they become incredibly luminous, and that's why they're known as active galactic nuclei. But how do they feed? So this one will not be uniquely so much about black holes, although black holes play the central role, pun intended. But feel free if you want to ask more specific questions about black holes as well. But I'm going to start off with a little bit of history for people to get a sense of how we got to where we are and why we even think black holes feed in the way that we think they do. So, over 100 years ago at Lick Observatory in San Jose, Fath noted that certain galaxies, when he took spectra of them, they had very strong emission lines. This was before the discovery that many knew, in fact, what the hell galaxies were. These were called, they thought they were the spiral nebulae. They didn't know, that the universe was much larger. And eventually they would become known as island universes before they even got the name galaxies. But they did know that there was a very sort of odd subset of galaxies based on their spectra. And so what do I mean by that? So on the lower left, you see what a normal galaxy spectrum looks like. That's basically the bulge of a galaxy or an elliptical galaxy. Again, it's just a whole bunch of stars, and a star's spectrum, the wavelength versus the amount of light it's putting out, is just the adding up of a lot of stars. And fundamentally, the spectrum of our sun or any star is basically a hot gas, and it has a cooler envelope around it, and that gives you these absorption lines. So it's a lot of dips in the spectrum. But if you have a particularly energetic situation, you don't get so many of the dips, you get these emission lines. So you get these spikes, which is telling you that there's something very energetic going on. So fast forward a little bit, nearly 40 years after what Fath discovered, there was a man named Carl Seifert, and he noted that there were several similar galaxies with bright centers beyond what seemed like the sum of their stars with emission lines. Which means, again, it's, if you added up how many stars you expected to be there, the light didn't match up. There was a lot more light coming out of the centers of these galaxies. And again, these had these, energetic emission lines. So it wasn't just sort of normalish stars, or what you would expect from just a lot of stars being packed together. And even then, the number of stars wasn't enough to make for that brightness. And so this was a project I was involved with many years ago now, looking at active galactic nuclei that were nearby. And you can see that, you know, it looks like somebody pasted a star at the center of these galaxies. They're just an enormous amount of energy coming out of them. In fact, many oftentimes outshining the galaxy itself. And so Carl Seifert had already noticed this about some nearby galaxies. So let's fast forward a little bit more, thanks to various developments in radar technology in World War II. Now there's the birth of radio astronomy. So now the wavelengths that we're looking at aren't just optical wavelengths. Now you can look at radio wavelengths. And so they started doing surveys of the sky. And the third Cambridge radio catalog came out. And there were a lot of interesting radio sources. And there were a lot of galaxies that seem to have this excess radio emission. And no one made really a connection with Seifert galaxies at the time. So here is a combination for Centaurus A. It's a nearby galaxy. And when you look at the radio, and you can see this, that's represented in green here, you have all of these sort of jets coming out, a lot of radio emission coming out from these lobes here. And so they were like, okay, well, there are galaxies that have these very odd excess extended radio emission. And then they were trying to match all the radio emissions to everything, to other objects at other wavelengths. And in 1962, they noticed that several of these, you know, radio excess objects matched to stars, which, you know, stars are not very bright radio sources. So people were very, very puzzled. They really couldn't be stars, but they looked like stars. So they called them quasi-stellar radio sources. And they look like this. So in the optical, it looks just like a star, but they had these radio lobes very similar to some of these other radio galaxies that people had already noticed. So it was QSRS, or quasars for short. That term came along. Again, nobody knows what any of these things are. Nobody's even linked what Fath had discovered, what Seifert had discovered, you know, radio galaxies. So it's just becoming very confusing. So then, in a very bizarre sort of set of unexpected circumstances, there was an observatory in Armenia, then this was Soviet Armenia at the time, called the Burak Observatory. And Benjamin Markaryan, he was actually assigned by the director of the observatory there. He was a graduate student. His name was Viktor Hambartsumyan. So they started doing they had a 1 meter Schmidt telescope. They put a prism in front of it, and they were looking for galaxies that just had excess blue light, essentially excess, basically UV light. And so they created this catalog of 1,500 sources of these very odd UV excess sources. And another person who was at the observatory, Edward Khachikyan, he was part of this US-Soviet scientist exchange program. And he literally took the catalog and brought it over to the University of Texas. And so that was the exchange that was happening. He worked with a graduate student named Dan Wiedemann, and they started getting spectra of these UV excess sources. And from 1969 to 1974, Khachikyan and Wiedemann published a whole series of papers and noticed that suddenly, you know, the Seifert galaxies, these galaxies that had excess energy coming out from the few that Seifert had identified originally, there were a whole bunch of them in this new catalog. And so they've generally become known as Markaryan galaxies, and you may know like Markaryan's chain and so on. So that there's a whole series of, even amongst amateur astronomers, that, you know, that are interesting targets to look at. So the state of play in the 70s was really interesting. So there was just this sort of weird taxonomy of all these different things that didn't seem to be connected at all. There was a large number of galaxies with radio emission from the third Cambridge radio catalog, large number of quasars, which in the 60s, an astronomer at Caltech, Schmidt, he had identified that they were very, very far away. That is, he got their spectra. Their spectra were highly redshifted, and this was already known that the redshift was correlated with how far things are because of the expansion of the universe. So quasars, these were, the reason they looked star-like was mostly because they were very luminous and very far away. So they weren't really stars, they were very far away objects, most likely galaxies. And so and then there's this large number of nearby Seyfert galaxies from the Markarian catalog, a lot of excess UV light, excess blue light as well. So it's a lot of, they're very energetic. And as they had been observing many of these, particularly the Seyfert galaxies and the quasars, they noticed that they were variable. That is, they were, the timing, and they changed over a short period of time. So, and that's actually a very basic physics argument that you can make, that things can't change faster than the light travel time. That is, if something's going to change, it has to communicate with whatever it is physically. And so since you can't travel faster than the speed of light, its physical scale, the time it takes for something to change, that is, if something is 30 light years across, it's going to take a good chunk of 30 years for the whole brightness or the whole luminosity of that thing to change. Because if something is changing in one portion, for it to basically communicate for those photons to travel out to say, hey, everything, start warming everything up, or things starting to cool down, the physical size of it will basically, dictate as to how quickly it can change. So if something changes on the order of a few light weeks, it can't be hundreds of light years across. And it also can't be, it basically has to be very small. It can be smaller than that, but then, but fundamentally it can't be very big. That was the thing. These things were very compact, very small. So what was the energy source for all these things? So at the time, it had been only about 20 years since they had figured out what was powering stars. The idea of fusion, combining two hydrogen atoms, or multiple hydrogen atoms to create a helium atom at the center of a star to provide the energy. That was the most efficient way people knew to really how to do that. But the problem was that, as particularly for these very far objects, which were the quasars, they needed huge amounts of energy. So you would need thousands of massive stars to be grouped together in a very tiny volumes to give you the luminosity of quasars. Also, but they were variable, so you can't have thousands of stars varying in unison. It's a little bit, think about your, Christmas tree. If all the lights are randomly turning on and off, the average brightness of your Christmas tree isn't changing. The only time your Christmas tree really changes brightness is if all the lights are turning on and off or getting brighter and dimmer. So if thousands of stars are just packed at the center of these galaxies, you can't have them very, simultaneously. They have to communicate somehow. And also similarly, they can only communicate at the speed of light. So that wasn't working. Also, if you pack that many stars together, gravitationally, they would disrupt each other. That's not going to work. Also, the most luminous stars are the youngest stars, which are the most short-lived stars. So you'd get a ton of supernova explosions, which would disrupt things anyway, but also you would get lots of, we knew what the spectrum of a supernova was. So that wasn't it. So what could be it? The only solution was accretion onto a supermassive black hole. So black holes were, strangely enough, actually theorized hundreds of years ago. I think it was, I want to say, I've forgotten, sorry. It might have been Descartes who even sort of postulated that, once, if you can have so much mass that you could pull light in, and so you would be, the most massive things would be the darkest things. But certainly, but Newtonian physics doesn't actually let that happen. Newtonian gravity is based on the idea that, if you know the formula, it's F equals gmm over r squared. But if you don't want to think about the formula, Newtonian mechanics is entirely about how much gravitational force one mass has on another mass. That's how he described gravity, which most of the time works fine, except light is massless. So if light is massless, it should not be affected by gravity. But when Einstein came up with general relativity and said, look, it's not the mass of something, it's how the mass changes the curvature of space. So it changes the environment around it. And so if something is curving space, then light or anything, a planet or an asteroid, will travel on that curved path. And then people said, well, if you curve it enough, then light can't escape at all. And so there was this whole discussion, and Einstein wasn't really keen on the idea of black holes, but Carl Schwarzschild did the math and said, no, this can happen. And everybody said, oh, that's just theoretical. it's never going to happen because you need to pack an enormous amount of mass into a tiny volume. And again, that's all a black hole is. There's nothing magical about what it is you take a lot of mass and you compress it enough so that the escape velocity is the speed of light. So that idea still existed, but nobody thought one could possibly exist. But then when people are trying to figure out how you get this much energy, the thing that you get with a black hole is whenever you are falling into something, you're changing your gravitational potential energy to kinetic energy. So if you drop your wrench and when you're working from 1 foot above the ground, it doesn't make it much of a noise. But if your wrench is falling from the roof, it makes a lot more noise because it's been accelerated more. There's more energy released when it hits the ground. In this case, it's being released in the form of sound, so much louder noise. So if you have a long, long, long way to fall because you have a lot of mass, but you compact it to a tiny volume, which means you will have a long way to fall, but you will also be accelerated an enormous amount because it's so massive, then you can get the potential to release an enormous amount of energy. And that actually, was something that people started thinking about, but then they were like, okay, so how are we even going to study this? How's this even? So if gas is falling in and it spirals into this black hole, so it has a long way to spiral in and it spins a lot and it liberates an enormous amount of gravitational potential energy by changing it into thermal energy, which is energy of motion. It can become very luminous. That's great, but how are we even going to study this? And is it even possible? And what's interesting, you would say, is like, well, why are we even talking about studying accretion onto black holes in another galaxy? We're in the Milky Way. There are black holes in the Milky Way. Let's study the accretion onto black holes in the Milky Way. And a lot of people did. And in fact, the very first really solid evidence that black holes existed and they were accreting was from a balloon-borne X-ray mission to try and detect X-rays from celestial objects, and they found the brightest X-ray source in the constellation Cygnus X1. And then when they looked at where it was a bright star, but it wasn't, the star shouldn't have been emitting that many X-rays. And when they looked at it, it was a binary system. But the companion was almost invisible. There was no companion in the optical light. But the other star, the bright star, kept orbiting something. And so that was the case where oh, okay. So there's gas flowing off of the main stars onto the companion, which once you did the math for it to, how much would it have to fall and spin and heat up to emit X-rays, it had to be a black hole, several times the mass of our sun. So that was great. It was a great, confirmation of this idea that yes, we can liberate an enormous amount of energy if gas is falling onto a black hole and it spirals in. Great, and these guys are nearby. We can study them, except unfortunately they're so small. It's really hard to study the actual disk. None of these disks have been resolved. They're just too small. And you would say, well, what about studying disks of gas falling onto the supermassive black holes at the centers of these other galaxies? Or at the time we knew there were black holes, and over time we've measured the masses, in fact, and known that they're supermassive. They're millions to billions of times the mass of our sun. And so how are we going to study this gas and just get any sense of how gas is falling onto a black hole? And in 1982, Blanford and Rees were studying, hey, you can do this thing called reverberation mapping. And this is where actually the variability of quasars and Seyfert galaxies and all of these things, which now the whole taxonomy basically collapsed into, they're all of these same thing. Some are more luminous and further away. They're the quasars. The Seyferts are the less luminous and the nearby ones. And so what it is what we know is that there's some energy that's generated from near the black hole. We don't really know what it is. In fact, the term we use for it is the lamppost because it illuminates the disk. So this is an edge-on view of this gas disk with the black hole at their center. So if that light generates from there, it's going to illuminate that disk of material, that accretion disk. And it's going to make it's going to put energy into that disk. So the first part that gets hit with that, big blast of energy from the central black hole is the UV emitting part. So you'll get an increase in the UV light. And then further out, maybe, blue light in the optical region. And then further out, there's the red light that'll come. So you can see that there's a time delay, that the shortest, hottest region, which emits in UV or blue, whatever region wavelength you're looking at, responds, reverberates that emit light first, and then the further out region reverberates next, and then the further out region reverberates later. And so if you do multi-wavelength monitoring, different filters, ideally starting in the UV, which you would need to go into space, which we've done, but still, you will get basically here, and this is actually, I've done this in the infrared, this is data that I got, this is optical light from the ground, and you can see that these peaks, the longer wavelength peaks are shifted later than the optical peaks. And here is one which was done by a combination of spacecraft, some observing the X-rays, Hubble Space Telescope observing at 1367 angstroms. And then there's the SWIFT spacecraft, which is doing 2 other UV more filters. And then it also has a U band, B band, and V band. And if you look at it, the peak basically shifts to the right, the longer wavelength you go. And the separation between them is a physical scale. It's a physical measurement of these different regions. So the light travel time between here and here, let's say it's a light day or 2 light days, tells you the physical scale of the accretion disk. So what we're doing, we're making a physical measurement of an accretion disk by exchanging basically time resolution for spatial resolution. So we're able to measure things that, only a few light days across an object billions of light years away. So what have we learned from, I'm not the only one. There's lots of reverberation mapping that's been going on. It's been going on for several decades. And so we have theoretical models of these disks that feed into the black hole, and they don't actually match the observations that we have. By how much? It's not a little, sometimes by a factor of 3. That is, the theory predicts a disk size different by a factor of 3 from the reverberation mapped size that we get. So what? Well, if we can actually match the theory to the observations, we can determine the inherent luminosity of these AGN. Because again, if you know this, surface area of the star and the temperature of the star, you can know what its luminosity is. That's sort of the basis of the HR diagram. But that's, very basic physics. The physics is a little bit more complicated here because it's not a single temperature across it. But if you can get the temperature versus distance for this disk, you can get the luminosity of these AGN. And Martin Schmidt, who discovered that quasars were these very far away AGN, there was a 50th anniversary event, and he lamented the fact that even though he thought, his discovery was very important, but the fact that we did not know the inherent luminosity of quasars, therefore we could not use them as standard candles. But if we know the inherent luminosity of the AGN, we can start using them as standard candles, and we can determine the distances to these objects in a completely different way. So this is an incredibly powerful technique. It has yet to, provide the final fruits of us to be able to really do a great measurement because it's very telescope intensive. But hopefully, as time goes on, we can start doing more and more of reverberation mapping for more and more galaxies and for objects that are further and further away. And that way, we can actually get a really great measurement of the disks that feed the black holes at the center of galaxies. So we'd have a fundamentally independent measure of the size of the universe. And that's it. And I'll start taking questions. And I see there are some in the chat already. So let me start off with those. Let's see. Okay. let's see, there's not necessarily all questions. Oh, short periods. So how long are the variability? Months, years, decades. So the variability depends on the mass of the supermassive black hole. And so, but also how the luminosity and how big the disk is. So for lower luminosity sources for nearby objects, the changes happen within a few days. That is, you're getting the arrival time between one wavelength separated from another wavelength is within light days to a few light weeks. Now, for quasars, which are much further away and their disks are much, much larger, that time difference is a lot larger. So that goes out to months to years. But yeah, some of them are really on the order of a few light days, and certainly between, like next to, UV and optical wavelengths is like within a day or two. That was for Terry. Steve Cooperman, S. Laplace. It may have been Laplace. It's been, oh no, John Mitchell first came up with the idea and Laplace ran with it. That's right. Okay, thanks, Tim. But Laplace actually moved it from later editions of his famous books on celestial mechanics. Interesting. Okay. So yeah, so it was interesting that people were thinking along these lines.
How long does it take for a black hole to eat a star next to it? Like when it's feeding on that, is it a long, long time?
Well, that's the interesting thing, and this is when the thing that I always mention, that black holes don't suck. That is, for a star, most stars just end up orbiting a black hole, so they never fall in or anything. But you can have stars that get too close and they get tidally disrupted, and that happens. The tidal disruption event actually and suddenly gets all this extra gas flowing into a black hole, and it's harder to see in already active galaxies, but we've seen quiescent galaxies. That is, there's no evidence of gas flowing into the supermassive black hole. So there's no excess energy. If you take a spectrum, it looks, like the spectrum of a regular galaxy. But we've seen those galaxies light up when they have a star that gets disrupted. And that happens, that disruption and flowing into it happens on the order of, usually the star has to come in close enough, and that happens over a few months. So the changes happen over a few months is what we see for what are called tidal disruption events. And these are usually shortened as TDEs. But we've now found a whole bunch of tidal disruption events.
So does the black hole like clear the center so that there's no more left to fall in?
Not really.
No?
No, the black holes aren't vacuum cleaners. That's unfortunately, a lot of scientists have said that. And we have a supermassive black hole at the center of our galaxy, and there's a huge number of stars very close to it. They just happen to be in orbit around it, and they're just not close enough for this sort of tidal disruption to happen. And that has to be, stars have to get really close to be tidally disrupted by the supermassive black hole. But this is what I joke about, that black holes don't suck. They're not vacuum cleaners. Most things end up orbiting them. Gas is the only thing that ends up accreting onto them, because gas has friction with itself, and so it has to lose orbital energy for it to fall into the black hole. And stars orbiting don't lose their energy any more than Mercury is losing energy to fall into the sun. It's or Earth around our sun. It's just we just orbit. And if the sun was magically turned into a black hole, it's not massive enough to end up in a supernova to become a black hole. But if the sun, we could, wave a magic wand, becomes a 1 solar mass black hole for our solar system, nothing would change about us. There's, Mercury's orbit would be the same, Earth's orbit would be the same, it would be very cold and dark. But at the same time, it would be, and that's the thing, is they don't really clear out. I mean, if things are in good orbits around, they're in 3-dimensional orbits around the black hole. And sometimes there's multiple interactions with a triple interaction between the black hole and 2 stars, and they kick out some of those stars. But usually over time, there's, things basically are mostly filled in, just like the center of our galaxy is not empty.
Can I ask you a question?
Sure, yeah.
Hi, I'll just lower my hand here. Can you talk a little bit about when they imaged the M83 star with the Event Horizon Telescope And I think they used the very long baseline interferometer.
Interferometry. Yeah.
And was that similar to how you're talking about those wavelengths being kind of like overlapped? I know they got many images and they overlapped them somehow. I'd like to hear you talk a little bit about how they were able to get those different images based on these wavelengths.
Sure. So first of all, it's not the wavelengths that they were looking at were radio wavelengths. Okay. And so one of the things that happens in, let me go back here. So radio emission usually comes from these jets that are material that isn't flowing in. This disk actually can get redirected by the magnetic fields around the black hole and be shot out into jets. And that's what these radio lobes are. But what they ended up doing with these, what's called the very long baseline interferometry. So the resolution of a telescope depends on how big it is. And it does not need to be entirely filled in. That is, we're just used to the mirrors being full mirror, which is great, but you can actually split up that mirror. And if you can combine the light the way the mirror would have had it been entirely filled in, you can get very high resolution. And so with what they did, which was what they called the Event Horizon Telescope, was they combined radio telescopes from all across the Earth to get the equivalent radius, or a telescope with the radius of the Earth. Now, it's not the same collecting area as the Earth. That means it doesn't catch as many photons, but fundamentally, it actually ends up with the resolution of a telescope that would be the size of the Earth. Now, because it's not getting the same number of photons, you need to look at bright things. And so in the case of M87, it's nearby, it's very bright. And so what it's doing, it's actually imaging this hot gas that actually is also emitting a lot of radio wavelengths right around the black hole here. So it's very close to the center. So they're not really imaging the disk that's of material that's falling in, but it's that gas that actually is very close in to the supermassive black hole. And that's why they called it the Event Horizon Telescope, because the event horizon is where photons no longer escape. And if Tim can chime him up, I'm going to stop sharing just for a second for Tim to speak for him, just because he has the picture already up.
Yeah, my background picture is the artificially intelligent, cleaned up version of the image of the M87 black hole that was just released. In every direction that you look at a black hole from, it will look like a ring, because the photons that close actually orbit the black hole. So you know things are weird when photons are going into orbit around you. It's not ordinary. It doesn't happen to the Earth, to anything else. But it's unstable orbits, and they fly out towards you in a ring shape, no matter what direction you're from. But the little bright spots like here, you can compare those in your image to a physical model of the black hole and decide what angle you're looking at. But it took them like 2 or 3 years to do that, because it's not easy. It's a lot of work to figure that out, and it's not necessarily unique. You got to test general relativistic models and stuff, and eventually come up with it. But
It's the shadow of the black hole, essentially, right? It's actually shadow.
The black hole itself is in here.
Yeah,
and we're seeing it's
what they
shadow,
call it.
right?
Yeah,
right.
That is what's interesting, is that although the M87 black hole is more or less pointed in our direction, no matter, like Tim was saying, no matter which direction you're looking, you're always going to see that, because it's basically has what's called a photon sphere, and light orbiting it. So it's a very, very odd thing that happens. But that's the thing. So what you're seeing is not the accretion disk, although M87 does have an accretion disk. But they were sensitive, and they were tuning their radio wavelengths for emission coming from right around the event horizon. So, but that was, in fact, although what I will say is everything I described was very strong circumstantial evidence for the existence of black holes. Now, circumstantial doesn't mean bad evidence. If you have, a friend staying with you and you have a cookie jar and then you see the cookie jar is open and there's a trail of cookie crumbs from that cookie jar to your friend and the friend has cookie crumbs on there, but you've never seen them actually eat the cookie, but you're pretty sure they ate the cookie. So in many ways, what we've been seeing is this sort of strong circumstantial evidence, and in particular for Sagittarius A star, which is the supermassive black hole at the center of our galaxy. We've seen the orbits of the stars, and we see very little emission from that center, but we can measure based on their orbits how massive it has to be. So that was incredibly good, even pushing way beyond circumstantial, but it wasn't direct evidence. The direct evidence for a black hole is the M87 image now, and then later on, the Event Horizon Telescope took an image of the supermassive black hole at the center of our galaxy. So those are the first absolute direct evidence of that. But the expectations are, again, how big is that shadow going to be based on the measurements we've done. We know what the mass should be based on, for M87 it was orbits of stars, which as well as the orbits of gas. But certainly for Sagittarius A star in our galaxy, we've been literally following the orbits of stars around it for decades. And one of the people who led that, who won the Nobel Prize for it, is Andrea Ghez at UCLA. So it's a big LA connection there. And so all of those had predictions of, if it's this massive, how big should that shadow be? And that was definitely a big success there. Let me go back, and I have a question from Arun. Do we know if the AGN of young galaxies are less massive than the ones in older galaxies? Is there a significant difference? Yes, it's harder to measure the masses of these earlier galaxies, but the expectation is that that's what it would be, in particular because we think over time galaxies merge, and therefore their supermassive black holes at their centers will also merge and become much more massive. But at the same time, it's a little bit tough to tell because, for example, the Milky Way is not a very massive galaxy, so it's the supermassive black hole isn't as supermassive as, for example, M87, which has gone through many, many, many more mergers. But the sort of general trend has been that for those that we can measure the masses, and it's tough to do as you get further away, that they can have lower masses. But I think that's still an open question to be settled, but that is the expectation. So let's see. Propreneur asks, how can you tell a black hole made out of antimatter from a black hole made out of matter? You can't. All you can tell is that there's a lot of matter there. It's unlikely that it was antimatter just because we don't have large amounts of antimatter floating around in our galaxy. We just don't see evidence of tons of antimatter around, because then they would constantly be annihilating with matter and creating lots of energy. But that's the interesting thing, is that, why is our universe biased so heavily towards matter versus antimatter? That's one of those really fundamental questions about the Big Bang, that there at some point something was shifted enough so that we're forgetting, sort of setting aside dark matter and dark energy, but fundamentally in terms of protons, which is the majority of what makes up the mass, it's mostly protons, not antiprotons. Why is that? That's a very good question to ask, and people have thought about it.
So does antimatter bend space-time in the same way that matter does? They're both just matter?
Exactly. They follow the equivalence principle. Their mass and the only thing that space-time cares about for the fabric of space-time is how much mass there is, and there's no difference in mass between a proton and an antiproton.
Yeah, that's the core of why we don't know, right? It could be, but we don't know.
Yeah. Let's see, what order of magnitude, so it's Terry asks, what order of magnitude is orbital velocity around a black hole? Does it get relativistic? Yeah, oh, absolutely, it does get relativistic. It has to, because once it gets to the event horizon, it has to be, it's the speed of light. But things become very complicated in some ways, because if you remember how one of the things that Einstein was able to show when he came up with his theory of general relativity with this idea that it's the curvature of space-time that is we experience as gravity, not what Newton called action at a distance, was that the orbit of Mercury is not what Newton's gravitational theory predicts. There is a precession in Mercury's orbit, which is just not accounted for by Newtonian gravity. It is accounted for by Einsteinian gravity because you have this thing called frame dragging. So as the black hole bends space around it, but the black hole itself is spinning and in fact spins space around it. And so as you're falling in, there's a point where you just start, even if you throw something directly into a black hole, it's never going to go directly in. As it gets closer and closer and closer, it starts spinning around because let's say you're throwing a hammer in. For the hammer, it's taking a very straight course into the black hole, but then the space it's on actually, even though it's still going in, it starts being dragged along. And that's our sun drags the space around it sufficiently so that we can notice that Mercury is being sort of pulled along faster than it would be just based on the mass and the distance between the sun and Mercury. So, and that gets added into the fact that as you get closer and closer, your orbit becomes faster and faster. And at the event horizon, the escape velocity is the speed of light. So it becomes incredibly relativistic. But also in this artist's animation, you can sort of see how you get all of these kinds of, weird wobbly things. That is, notice that the black hole doesn't block the light from behind it, because what it does is it bends the light over itself towards you such that you are seeing behind the black hole, even though you're looking directly at the black hole. So these are all incredible relativistic effects that happen near black holes. Near black holes, event horizon has to be close to the speed of light, relativistic. Yes, Keith. Funny that the shadow is the part with the light in it in this case. Yes. Let's see. Terry asks again, how fast have we measured orbital velocities of stars here? Do we see spectral lines highly tilted? Yes, that's the thing. Is, for example, for the M87 black hole, Hubble was able to measure both the gas velocity and, in fact, the velocity of stars based on the Doppler shifts of both the gas and the stars. We have directly measured, we directly see the individual stars going around Sagittarius A star at the center of our galaxy. So we just, it's time versus distance, we know, and they're incredibly high velocity stars.
Doctor, I have a quick question.
Yes. Go ahead.
Yeah. Thank you. I'm looking at the, is that a quasar that's coming out from this representation here? That's coming from the center outward?
No. So what this is, so the quasar would be what we would see from light from this disk.
Okay.
So, in the sense that that's sort of the luminous star-like part. That's the star and quasi-stellar part. The radio source part is, so would be coming primarily from this jet. So that's this part. That's this jet that you see here. And
okay,
for example,
is that being pushed out? Is that being pushed out or being sucked in?
That's being pushed out. That's a very odd thing that happens. But think about how the magnetic field of the Earth is, or a magnetic field around a bar magnet. There are closed loops, but then there are open loops. And so this becomes highly ionized gas, which means it's very magnetic, and it can be redirected into these poles away. So these poles are actually symmetric. But what's interesting is that if that's one of the poles is slightly directed towards you versus slightly directed away from you, there's what's called relativistic beaming, because the particles that are being accelerated are getting very close to the speed of light. And so because of relativistic beaming, things that are coming towards you get artificially brightened, and things that are going away from you get artificially dimmed. And so even though this is a symmetric thing that you should see both, going both to the top and away, but the reason I know that this top one is tilted towards us, and this little bit of a brightness here is sort of the tip equivalent of this one going the other way, is because of relativistic beaming. So this is very symmetric. And in this case, when we're looking at it edge on for Centaurus A, you can see that it goes both ways, but even this one is slightly tilted away from us, so it becomes much dimmer, much faster. But that's the radio emission part. And that was, again, it was very hard to put all of these things together, but it does all come from this idea that if you have gas falling into a black hole, it flattens into a disk, becomes incredibly hot, but towards the very end, it actually, some of the, not a lot, but a very little bit of it can get redirected. And in fact, there can be clumps that are artificially excessively bright. And Philip Taylor says synchrotron radiation. Yes, this was primarily synchrotron radiation that's coming. Synchrotron radiation comes from charged particles spiraling in magnetic fields. And that's exactly what this is.
Thank you.
Have I gotten, I'm not sure if I've gotten all the written questions, but if I haven't, please, there's somebody that can. What do we see of mass increase at relativistic velocity? I don't think we really have seen, so as you push things to go faster and faster and closer to the speed of light, you get an increase in mass, and I'm going to oversimplify things in some ways, but but everybody knows E equals mc squared. So the way to think about it, one way to think about it, not correct, but sort of gives you a general idea, is so if E is energy equals mass times the speed of light squared. So if you're increasing kinetic energy, you're actually increasing E. You're not, but for that equality to remain an equality, something has to increase. And that's actually the mass. So in our accelerators on the Earth, when we actually accelerate particles, we get the sense that the greater energy that you're putting into it is equivalent to that particle as it's moving faster and faster, becoming more and more massive, because it has that extra kinetic energy, which is the equivalent of mass. So we have not really seen that we're not that sensitive. This is a much broader scale kinds of things. So we don't see the mass increase in terms of relativistic velocity from things accreting onto a black hole, nor if they are, particles being beamed in our direction from the jets.
Well, it looks like that might be all the questions.
Somebody
else pop up in there?
Oh yeah. Philip asks, as activity gets closer to the event horizon, does it become a hologram to an outsider observer? Richard? Well, I'm not sure how I could necessarily say it becomes a hologram, but it for sure becomes redshifted. That's the thing, is that as material is falling in, that is going to be, significantly redshifted. Again, if it's if you're looking at it essentially edge on, depending on where the disk is, because if it's face on, you really aren't going to get redshifting in terms of, well, what you get is there's a velocity redshift and a blue shift. We can see that around nearby AGN. And then you have, there's gravitational redshifting, but that's really coming from stuff that's very close to the event horizon, to the point of it really being it's going to get overwhelmed by the luminosity of light coming from the accretion disk. So you're really not going to get a sense of the gravitational redshifting, because that does happen as things fall in. Again, they're being accelerated away from you, just like any kind of Doppler shifting, it gets, redshifted. But anything that's falling into that last bit, it's very hard to detect that versus all the light that's being generated by the accretion disk around it. So it's going to be very difficult to detect something, the redshift of that. That's just going to get lost within the redshift and blue shift of the gas disk spinning.
Yeah, to an observer far away, if you have a nice quiet black hole that's not doing anything, if you watch something fall into it, the redshift, gravitational redshift becomes infinite, and you never see it fall in. It will just hang there eventually, just disappear. But if you're doing the falling in, that won't happen. You'll fall in. But if you're watching Don't jump into a black hole. Bad idea. But if you're watching from outside, nothing ever gets in.
Yeah, but that is, if you want to sort of get into a lot more of the details of this, remember this is space and time. So space-time gets stretched. So time is getting stretched. So what's called, there's time dilation in addition to the redshifting. And so as you're falling in, if you're looking at somebody else's watch who's falling in, your watch says 1 second per second, and you're looking at somebody else's watch who's falling in, their watch starts ticking slower and slower and slower and slower. And then again, and their light becomes more redshifted, so that whatever colors they had, they become redder and redder and redder. But then they basically freeze up to the point where they just it looks like they're hanging there, and then their light gets infinitely redshifted and you don't see them anymore, but you don't really see them fall past the event horizon. For the person who's falling in, though, they're looking at their watch and their watch just says 1 second per second, and they're looking at the watch at the person who's further away. And this was, by the way, very well represented in the movie Interstellar. That is, those people who went closer to the black hole, their watches ticked slower, and so they aged less than their colleague who was further out. But if they could look at the watch of somebody who's further away from the black hole, that other person's watch starts ticking faster and faster and faster, versus yours where you're thinking, oh, this is still 1 second per second. Well, you're welcome.
Fantastic.
Yeah.
Fantastic thing.
And if you really want to learn a lot about black holes and you're crazy, this is the book you need. David Meyer was another of our colleagues at JPL who wrote a book about the astrophysics of black holes. It's nearly 1,000 pages long, and it'll hold down your desk in a stiff wind, but like good black hole will.
And he cut it down.
Yeah.
The publisher said it's too long.
Can you put that reference in the chat?
Yeah.
Oh, you want to read it?
I don't know. I'll let you know. I'm gonna probably get it and see what happens. Maybe I'll fall into it real slowly.
Okay, really, really good. Thank you again. I dropped the form in the chat for the drawing that we can do at the end here. Any other questions for myself or Tim or anybody else?
I have one last question for maybe. Currently, what are you looking for? What's the newest thing what are you trying to find out now? Like, I mean, from everything that you already know and understand, is there something new that you're working on now that JPL or?
Well, it depends. I mean, on the AGN front, my sense is to really push reverberation, to really get a much better, much larger sample, but much better measurements of the disks, so that we can match the theory to the observations, so that we can actually so we can eventually use AGN as standard candles, because they're all over the place, and some of the furthest objects that you can see are quasars, so you can really map out the entire universe. And although there are very good other techniques, but the best other technique is this supernova technique, so you keep having to wait for supernovas to go off. But not that that's a bad thing. I mean, they've gotten that down very well, but I think it'd be great to have a completely different method for a distance measurement. But for that, we need to get a lot better at reverberation mapping. And I'm trying to get a mission that's dedicated just to reverberation mapping to go forward. It'll be a small mission. It wouldn't be that big, but sorry, go ahead.
I'm just saying thank you very much for your talk tonight. It was great.
Oh, you're welcome. No, yeah, sorry. But yeah, but look for, like, James Webb will be studying a lot about the specifics of how the gas really flows into AGN, and also picking up some of the earliest galaxies. And we know somehow supermassive black holes are look like they're at the centers of all galaxies. This chicken and egg question is still not settled, and it'll be really interesting to get a sense of how these very early galaxies are, being, how they're interacting with the galaxies. And again, we know eventually they have multiple mergers and so on, but that's a really interesting question. How do black holes and galaxy growth go together? And I think that's one of the key other questions and James Webb is particularly well suited to address that.
Great. Thank you so much.
You're welcome.
Great. A lot of kudos in the chat also from me. Sorry. Put this off.
I think Daryl got sucked into a black hole.
I think so.
That was Mr. Bill, not a black hole.
Sorry, I was just coughing. Well, let me turn it over to Alicia. I saw her here somewhere, and at some point, let's see. I give it about another couple of minutes, maybe a minute or two for anyone else to sign up. Drop it in chat one more time for the link.
This is the lovely Veronica, everybody.
She looks very excited.
Happy new members. And I see you guys on Wednesday, yeah?
Yeah,
Good.
they were at Garvey last Wednesday.
Yeah. Okay, I'm closing the forum. I'm gonna go get the names off of the forum.
I put the book references in chat, but be mindful of the fact that those are like real physics books. So if you're not a serious mathematician and a serious physicist, you're going to have a hard slog.
So it's a textbook. It isn't
That's
general
right.
reading.
Yeah, but if you actually, let me put another reference here. I think it's called The Science of Interstellar.
Yeah, I think I've seen that.
Yeah. So that one actually is more non-expert friendly. It was written by Kip Thorne, who also won the Nobel Prize.
Yeah.
That was about how gravitational waves are generated when black holes merge. That's the sort of ripples in space-time. And he was the science advisor for the movie Interstellar. So if you go there, Kip Thorne wrote this, and it's a lot more sort of conceptual description of what it is, and I actually find it quite useful.
Okay, here's the spreadsheet. I'll drop the names in here. Okay, Borislav is our first winner.
You there, Alicia?
Alicia's
Yeah,
here.
I'm here. I was
There she
copying
is.
down the books that Tim posted. I was like, is this graduate level physics or is this college level or doctorate level? I was trying to figure out what kind of math it was on
PhD
it.
level.
Yeah, Meyer's book, is an undergraduate could probably get something out of it. Chandrasekhar's books, to read his book.
Okay.
Can you repeat that last sentence, Tim? You gobbled up for me. I didn't hear that again.
Chandrasekhar's books are mostly all insanely mathematical. So even if you think you know physics, and you probably do, the mathematics is impressive. His book has the longest version of nothing that I've ever seen, an equation that fills up an entire page and then is equal to zero, right? Because the mathematicians do that kind of thing.
Yeah, I remember that in college. Every
Right.
midterm.
Okay, so you got the first one, Alicia?
What did Borislav win?
Star Civic, I think is.
Oh, you mean he won something?
Yeah, he won a $25 Amazon gift.
Okay.
Hey,
Cool.
spend it on my piece.
Okay, Andrew Jones.
Beginner's luck.
Did I see a name pop in there before that? Did I see Terry Koken? I think I did.
I did. I think we got Terry Koken and then Andrew Jones.
I think you're right.
Maybe because you deleted a person in the entry. Because every single time you delete a line, it auto updates.
I understand. I only deleted the name though, so I deleted it again. The
Oh.
line. I didn't delete the line the first time, just the name. So we got Terry Koken won something first.
Is he?
Ugh.
I can't find it. Okay. Ted won a red flashlight. There we go.
Red flashlight coming your way.
Thank you so much.
You're gonna need it at a dark site. Oh, really?
And,
I know.
And what about Andrew? What did he win?
Andrew won a Celestron Observer's Map of the Moon.
That's good.
Cool.
That is good.
You're gonna need one. Good
I'm gonna
stuff.
delete Terry
Yes, we are.
and Michael Martin.
Michael won a gift from the LAS store.
Nice.
Let's see, where is he? Way up here. All right. I'll send you the emails of everyone here.
Thank you.
And Michael, then Bill Taylor.
Phil
Oh,
already
so
has
what, huh?
everything.
He's had everything for so long, he needs a new one.
Yeah, he's in replacement mode now.
Yeah.
Phil won the Northern Summer Sky and Astronomy Constellation tumblers.
Okay,
Whatever that was.
I think he'll need that.
They're constellation tumblers. There you go. Your drinking glass.
Oh, tumblers. Okay.
Yeah.
Cool.
Probably wrote it.
Okay. How many more?
One more.
One more. Okay, so last one. Steve Cooperman.
Ah, Steve. You want a ticket to the planetarium?
And what did
show?
lovely Steve win?
Steve won the Skymaster 15x70 binoculars.
Hey, some new binoculars.
Ooh.
Cool.
Oh, that's
Wait a minute,
great.
Did you say 50?
15.
50?
15.
15 by
70.
Yeah.
Oh, God, those are. Wow.
Thank you
Okay,
very
thanks,
much.
Alicia. Thank you, everyone. So that's
Oh,
it.
yeah. Those are big.
I can
Did
stop
Terry
sharing.
Koken win something? And if so, what?
Yeah, so I stopped sharing
Mm.
the last things in the chat. Okay.
Yeah, I think she said that Terry won a gift from the LAAS store.
Right.
Oh, did he? Okay. That's good to know.
That means you log in and buy the most expensive thing you can find, and it's on us.
I had Terry Koken as winning the red flashlight.
Oh,
The
okay.
red
That's
flash-
even better.
Is that right? Oh, great. Always wanted a red flashlight.
And I think Michael, I mean, Leisha's the official thing. I just kept some notes.
Yeah.
I think Michael Martin won the object from the store where you can go
Ah,
find our expensive hoodie, order a decal or a mug or something.
Yeah. Yeah, the mugs are cool. I've got some of those.
Oh, you guys are shameless.
I want to see the tumblers. So next time, Steve, you got to like pour yourself a whiskey and hold it up at the next meeting so we know what's
Hey, that'd be cool.
Who decides what prizes are in these giveaways?
Alicia has a budget for prizes for the door prizes, and she has some sources. I don't know. She finds sources for things. That's her job.
Ugh.
And I think Alicia and the board are always open for suggestions if you want to mail one in.
Just send them my way.
Yeah.
Did you have a suggestion for something that we don't give away?
Well, I was just so disappointed with ZWO's offerings today. I thought maybe we should just give a C-Star away every month.
An optimist and a
Oh,
dreamer. I like
no.
that.
You
Sure.
could you could donate yours and we'll give that away.
Yes.
Making all that frustration off your hands
I didn't
immediately.
pay. If I have a C-star, I didn't pay for it.
Okay, well, I think we can officially end the meeting. I think we're done with all of our business. But we certainly will leave the Zoom going and people can chat after here. So we'll